this example, we have a 10 centimeter long wire. It's being pulled along a U-shaped conducting rail in a perpendicular magnetic field. So this applies to the sorts of things we've been looking at so far. The total resistance of the wire and the rails is 0.2 ohms. When we pull the wire at a steady speed of 4 meters per second, we cause a power dissipation of 4 watts in the circuit. We're asking for two things: how big is the pulling force, and what is the strength of the magnetic field? So let's start with a sketch of what's happening. So let's draw in our circuit. Here are our conducting rails. Here's our bar. And let's put the magnetic field in there too. Maybe I'll even just color that in a bit so it pops out a bit more. Our magnetic field, we've done into the page so far for everything. Let's do this guy out of the page. Doesn't really matter what we pick. Just have to make sure we show what we're doing. And we're pulling it along, so let's label in a velocity there. There's our velocity. Let's say we're pulling it to the right with a speed of 4 meters per second. Let's make a list of all the things that we know. So the length, the part that's in the circuit in our field, that's 10 centimeters, 0.10 meters. The resistance of the whole thing is 0.20 ohms. The speed at which we're pulling it is 4 meters per second. And then the power, a little bit careful here, the power is dissipated, so it's minus 4 watts. So now let's think about all the things we know about this kind of motion. If we think about pulling the bar in the field, we know that we get an induced motion of the charges. So we get an induced potential of B times L times V. We'll put induced in brackets here. If we get an induced potential, we get an induced current. And I know we've just gone through this, but sometimes it helps to hear it again, just in case it was a little bit not quite so sure. So current is potential over resistance. That's Ohm's law. This is our induced current. What do we have next? We know that the induced magnetic force is IL cross B. Everything's perpendicular, so the magnitude of the induced magnetic force is I times L times B. Put in what we have for our current, BLV over R times L times B, gives us B squared L squared V over R. There's our induced magnetic force. And let's also write down our power. So there's our induced magnetic force, FB. Next we'll write down our power. Power equals F dot V. So the power dissipated in the circuit comes from dissipation by the magnetic force. So I'm going to put a B on this guy, equals minus. Okay, so let's just pause here and ask where we're going to go with this. So we've written down a lot of things. Now let's try and find our answer. The first part is how big is the pulling force? Well, right off the bat, we don't have a pulling force written down anywhere. We have a magnetic force. So why don't we draw a free body diagram on that bar and ask how are we going to find the pulling force? So I'm going to go onto a fresh sheet of paper. Here's our bar. We're pulling it to the right, so there's a pulling force to the right. There's an induced magnetic force to the left, FB, and it's going at a steady speed, a constant speed. If we have a steady speed, the acceleration is equal to 0. If the acceleration is equal to 0, then the net force is equal to 0. So minus FB plus F pull equals 0. So the pulling force is going to be equal to the magnetic force. Okay, that's good to know because we were asked for the pulling force. So now let's go back to what we wrote down a moment ago and ask, can we find the magnetic force? Well, yes we can. We know that we have a power of minus 4 watts, which is equal to the magnetic force times the velocity, the scalar product. So power equals FB dot V equals minus FBV, okay, minus because the velocity is to the right and the magnetic force is to the left. Those are in opposite directions. We'll put our numbers in here and we see that the magnetic force is minus the power divided by the speed minus, okay, and careful here, our power is dissipated, so it's minus of minus 4. Divided by our speed of 4 meters per second, we get that the magnetic force, the size of the magnetic force is 4 over 4 is 1 Newton. So that means then that the size of our pulling force is also 1 Newton. If you were asked for the pulling force as a vector, then you would say that your pulling force is 1 Newton I hat, or in the direction of motion. Okay, so we set up the problem first and then we got to our answer. The next part, what is the strength of the magnetic field? Well, we can come back to that power expression. Power is force times velocity, and force is B squared L squared times V over R. So we can put those things together. So power, so that was part A, this is part B. Power is equal to minus FB times V. F is equal to I times L times B. I is potential over resistance, and potential is BLV, so we get this expression for our force. So we get minus B squared times L squared times V over R. So there's our force, multiply that by V, so we get minus B squared L squared V squared over R. We're trying to find the size of the magnetic field, so B is going to be minus P times R divided by L squared times V squared. Take the square root of the whole thing and put our numbers in, so minus 4 watts. Resistance 0.2 ohms. Divided by L squared, that's 0.1 meters squared, times V squared, that was 4 meters per second squared. Put that through the calculator and we get a magnetic field strength of 2.24 Teslas. Okay, next we'll be ready to move on to another section.